Hey folks, I'm starting like literally 2 minutes early just to see if everything works everywhere. I know that there is a delay, but I want to check if the chats are working. I know that you will be able to ask questions on YouTube and LinkedIn because I already tested that. And I'm actually not 100% sure where you can ask questions on Facebook. I just yes, awesome. So it seems that you can ask everywhere, and it works. So that's great. So hi and welcome. Let me just close a few things, and we'll be ready to start. Uh, this is a simple open Q&A session. So the idea is that you will ask questions, and I will do my best to answer them. Since internet is full of random people, if you haven't met me already, my name is Łukasz. I have a PhD in shell stability. I own an FEA design company. I've been doing that for like 15 years now. For a decade, I've been a lecturer on structural steel in local technical university. I run a blog on enterfea.com/blog, and I also do trainings, company training, online training, and stuff like that. So yeah, I hope that this shows that there is a chance that I will know what I'm talking about. I'm doing this Q&A mostly to celebrate the fact that I just started a new email series that I'm very happy about. And I even created a 1-hour lecture that you can sign up to, and then you will be added to the email series as well as an incentive. So you can go to enterfea.com/video and sign up there. It's a pretty cool lecture on nonlinear material, and I'm pretty certain that you will like it. So I left myself a place where I can draw, and it seems that we are ready. Q&As are usually starting slowly, so to give you a chance to ask questions, I also asked people to send me the questions beforehand, and I actually got quite a few of those. So I will slowly go through the list of the questions I got by email or messages, and I have to admit that I haven't read some of those yet because I just realized that there are like comments on Facebook and I haven't got a chance to read them. So I just printed them and I have them in front of me. So I will start there. And if you have any questions, you can write them down and post them in the chat. I will see them. I am also able to display them like this. Hey, Carl, by the way. And we can all have fun, I hope. Okay, so the first one is how to calculate the optimal load step for any applied load. When you're doing a nonlinear FEA, you will want to divide your load into load increments or load steps if you prefer. And as you set up a nonlinear analysis solver, you actually need to decide how much of the load should increase every step of the analysis. Clearly, you don't want to apply everything at once because that would be very difficult to converge. Although there are some rules I will mention, I have to start by saying that there are no gold rules on how to do it. So the best way I think about it is that when you're starting an analysis, it's a good idea to be aware how much capacity you should expect, or at which load level something will happen. Of course, you will never know this perfectly. Like there is no way you could know the answer, then you wouldn't have to analyze it. But you should at least have a vague idea on how this would run. And then you should apply load that is higher than whatever you anticipate, right? Let's say that I foresee that a vessel that I'm designing will fail on the external pressure of, I don't know, 10 kilopascals. Like there's a very low level, but whatever. And then you can say, okay, I will apply 50 just to be sure that the load that I am applying is actually higher than what I'm expecting. And then the load step I would make would be something like, I want to have around 20, maybe 30 load increments before the moment I anticipate that something will happen. So if I anticipate that something nonlinear, maybe a collapse, would happen around 10 kilopascals, I would make a load step of around 0.3 kilopascal. Because then with this load step, I get like 20, 30 steps, maybe slightly above 30 before the failure actually happens. So this gives me like a nice step into the analysis. You don't want to have too many of those because it will take ages to compute without any good reason whatsoever. But you don't want to have too few, especially if you are using something that allows the solver to change the load stepping. For instance, you have like an automatic load stepping scheme, and then your solver can speed up or slow down analysis depending on what is going on. You don't want to have too few steps before something important happens, because this may cause your solver to get stupid. I will prioritize the questions I get live, so I will ask them as they come and then go back to the list whenever we'll have a chance. So Milad asks, how a nonlinear analysis solves singularity problem? If you're talking about stress singularity, and I assume that you do. By the way, I hope that you hear me all right. If you have any sound issues, please let me know in the chat. If you're having a stress singularity of some sort, when you're using nonlinear FEA, then you can, assuming of course that you have a material that can yield, then you can say, okay, for a very high strain level, please respond with a yield stress instead of infinitely high stress. By this, I mean, up to a certain point, your material gets a Young modulus, so it's the linear part. And then afterwards, you just get a plastic plateau, assuming that your material will yield. So if in linear FEA, you would get like a huge stress that is unreasonably high, what you actually get is an unreasonably high response to a strain that you got in that level. So if you would have a decent strain, this would still respond, the structural response of the material would be with yield stress. So you wouldn't have stresses higher than yield. Although you still may have issues with converging the values of plastic strains in a given place. So this means that even in nonlinear FEA, when you have like a very big concentration of whatever, in that area, you can have a very high plastic strains, and you will still have to deal with this somehow. And I actually did some laboratory tests on samples recently for my nonlinear course, where I built models purposefully to concentrate plastic strains to see what's happened. And the tests show that very high, very local plastic strain concentration is most likely not very dangerous, but I have to admit that I'm still in the process of dealing with the outcomes. So I don't have the conclusions yet. Which book would you recommend for someone who is starting to learn FEA? Victor, that's a very tricky question and a difficult one to answer. I'm not a big fan of FEA books in general. I think that they are way too theoretical, and I have like entire shelf of those, to be honest. And in every book that I've read, I've missed something, and mostly it's like the practical things that are just not there. So it's hard to pinpoint a book I would recommend. Of course, you can read the Dominique Madier book on FEA. I think it's the best I've seen, although it's very hard to teach the practical aspects of FEA in a book, because that's done with examples and showing live how to think about stuff. It's hard to describe it without, writing you a manual of click here, click there, you clicked there because of this and that. That would take like hundreds of pages without much gain. So it's better to like shoot a video while doing something and commenting as you go. So books are tricky, but you can definitely check Dominique Madier book. Like, I think that it's the best on the market when you're searching for a book. But if you really want to learn how to do practical design, I would rather think on courses rather than books, to be honest. How it would be to use a gap element with or without initial opening in the modal analysis? I'm not absolutely certain if you could. I mean, modal analysis is very similar to linear buckling in this regard, and it's like a linear process essentially. So in the end, I think that what the analysis would assume is whether or not the gap will close, and it would treat this element as if it's there or as if it's not there. You can't just make a model or linear buckling analysis saying something like, okay, if this shakes or buckles, whichever be the case, and I have a support 10 millimeters away, if this moves those 10 millimeters, it could touch it, and then like this prevents further shaking or buckling, right? This won't work. It's a linear algorithm. So you would need a way better solver to do this. It would require like non-linear buckling in case of linear buckling, and force vibrations in case of model analysis. Like model analysis itself won't be able to do it. I don't think I ever saw a software that would be able to do that. And like, I don't think it's possible technically. Like, it's not like the software is stupid. It's like the model analysis just won't be able to deal with that. When a rocket is in the air, which location one should constrain to have a action-reaction equilibrium? Wait, I'm a civil engineer. But it would be, I guess, what you're aiming at is applied load equilibrium. So you would have to figure out which forces actually work on your system, add all of them so they are in equilibrium, and then just do like 3-point restraints to block the rigid body motions like fakely. Because if you think on it, the support is essentially a reaction force. So it's a force. So you could take the support away and put a force in, and like the thing is still in equilibrium. The problem is that you get rigid body motion, so everything goes south, right, for 2 kilometers or something. And if that would be the case, then the problem you're getting essentially is that you are trying to calculate a model that is perfectly in equilibrium, but the solver doesn't like it because it floats in the air. And then like supporting the rigid body movement in 3 points that simply block the possible movement and rotation, I guess would be decent enough. Although I am aware that when you design a ship, you can literally have like a pin support on the tip of the wave on one end of the ship and the other end of the ship. So I guess that when you're designing a rocket, there are like magical things people do that simply make this happen. But I'm not in this field. I've never designed a rocket, so I don't have any practical experience to share the jokes with you about that. What should we do to progress in our career as an FEA engineer? Whoa, that's a difficult question, mate. I guess that FEA doesn't really differ much from any other type of a career you may have. And there is a difference having a job and having a career. FEA actually allows you to have a career. I would guess that getting better and better at it, this way or another, would lead to a better career in the long run. Assuming, of course, that you have a character that would allow you to base yourself and your situation on what you actually know. So you would have to be like self-confident and be able to say, yeah, I can do this, right? I'm able to do this. I'm not the best person to ask this actually, because I have to admit that I started my first business when I was fresh out of college. And I have a wonderful wife who's in IT, so I didn't starve when I started my first business. And that's also important. And when you have your own business, it's easier to do what you're interested in and scale whatever you do, hire people, develop a company, and so on. And also to simply excel at something. The problem I think you may encounter, or maybe not, would be like your boss not caring whether or not you're doing something correctly. They just need you to do it quickly, for instance, right? It's very hard to develop skills in circumstances like that. And this would be difficult. But does it mean that you should instantly change your job if that's your case? Like I'm I'm in no position to give you advice on career. Like, I don't know you, essentially. But I really strongly believe that developing your skills and investing in what you know, thinking what you're doing, and being like honest would actually be enough. And that would be my approach. This is how I develop my companies too. So if I don't know something, I just say I don't know it, and that's okay, right? I search for people who know. I don't neglect things. I don't ignore things. I just pursue them to whatever end those things may lead to, and that would be, I guess, the advice. Although, you know, it's a topic for hours and hours of conversations, and those would very quickly end up to be philosophical and like sociological in nature. And in the nonlinear course, we have like bi-weekly meetings where we talk, and very often the topics tend to go toward like philosophy and psychology of life, and it's just one of those. And in the end, I'm sitting here with a very fancy office background behind me, so it might seem that I'm like a super smart guy to ask for career advice because I've made it. The problem is that there is something called survivor bias, and whatever I would give you an advice on, it could happen that just as I started my company, 1,000 people following the same rules started the same company and failed, and I survived. And now I'm telling you, oh, this is a great advice because it worked for me. But what I do not know is that maybe it didn't work for like hundreds of other people. So giving like general life advice is very tricky. So, but still, I think that developing your skill is a good advice, like regardless, and caring and being honest. That in the long run, that should suffice, I hope. What can cause a stress singularity? Oh, that's actually easy. There are plenty of things, of course, but the most classical one would be like an inside corner of hate, where you have a rectangular cut in your model, and this inside corner is there that would cause a stress singularity. Or if you use a point load or point support in one node somewhere, that would be like the perfect example. So this usually comes from simplification of the models. Not all of them are bad, because sometimes it makes sense to make a point load in your model, even though you know that it will cause like a stress singularity in the support. If you don't care about this area because you want to analyze the different area of your model, that would actually work. So, yeah. Great work. Thanks, man. I'm happy. Thank you. What can cause a stress singularity? Oh yeah, I just said that. Lorenzo asks, if you have a clumped beam. Oh, like this is the problem with questions like that. I do not know what you mean by clumped, man. Like this, I can translate the word to Polish into my head, but it's like there are so many specific names you get for different types of supports that I'm already like afraid of the question. But let's move on. Maybe it'll become clear. If you have a clumped beam and I have a load that is a function of time and even space. So it's a pressure load for a transient analysis, how I should consider. Is it important, the distribution or not? Okay, so gladly we are past the clumped beam, because I'm pretty certain that whatever you may think clumped mean in terms of support, it's some sort of beam that's loaded. And your time change in function of time and space. By space, I assume that it's not like a uniform load, but it changes throughout the length of the beam, right? So, well, you should have a function that basically changes your load in time and space, and then you model the load in the domain of time and just analyze this. And of course, the load distribution will be important. I mean, you can have a lot of load on the left or a lot of the load on the right, and depending on how this changes, that would influence the outcome, right? But I'm not 100% sure if I understand the question, to be honest with you. I think that the problematic part might be to figure out a way to mathematically describe the load changing in time. And that would be something like figure out in which areas the load can be treated as more or less constant, because otherwise you will get to mathematical functions that changed in time. And that's like, I don't like high mathematics. So I would try to divide the load into chunks that I can consider like relatively small areas and then write a time function for each of those loads. And then all of those loads changing in time and then changing in space because you divided them would do a trick, I guess. I have to admit that I rarely, if ever, meet problems like that in what I do at work. So I never had to figure out like a nice automatic way of doing that. Oh, I just moved my mouse to see the next question and I realized that we already have like 40 of them. Okay, so that's awesome. And by the way, I'm really glad that you are all here with me. I really appreciate that. That's so cool. Thank you for taking the time. What is some best practice for preparing sheet metal models for analysis? Adam, that's a very nice question. And actually, it's like close to what I do. So first of all, this depends on whether you did the model yourself or you got the model from someone else. And like in my line of work, I would get the STP file with 3D geometry from someone else. So the first thing when I prepare a model would be to watch the 3D file and search if I'm absolutely certain where this is welded and where it's not. And that would be a huge thing because usually in those STP files, you don't see the welds, nobody models them, and they shouldn't really because why bother, right? But asking, okay, is this welded or not becomes a very big thing, right? Because it would impact how you model things. I've seen situations when you have a plate that is like literally bended backwards and not welded. So it's difficult to model it because effectively you have two sheets with contact with one another and nothing else. So that would be a good thing. And then I would remove a lot of details. Oftentimes you will have like notches to help bending and maybe some cuts and preparation for welds and all that stuff. You just have to remove those. The big issue would be, especially when you're connecting plates with different thickness, they are aligned on the surface that was needed to be smooth, and on the other end you had the jump, right? So you need to carefully plan ahead where those jumps are and which surface you wish to model, because you don't want to have those jumps in your model, most likely, unless there is a very specific reason for them to be there. So that would also be something I'd pay attention to. And then, just model meet surfaces and nicely mesh them. Depending on what size, I would say size of the model you have, then usually the bands of the flat plate steels are rounded, right? It's not like 90-degree band. There is a nice round at the corner, and you may want to remove those if you have a huge model, because otherwise if those cross in like weird angles, you have terrible geometry there, and playing with that is a huge hassle. I don't think it's worth it. So, but if you have a small model, like those details may actually be important, right? It depends on the engineering case, really. So I think those would be the most important parts that, like, rapidly come to my head. How we deal with geometrical nonlinearity and contact nonlinearity in the same model when we are doing nonlinear analysis? Well, you just run the analysis, mate. I mean, the convergence will be a problem, right? Because normally when you're doing only the contact analysis, most likely the contact iterations happen at step one of the load, right? Like in linear analysis, at the beginning of the analysis, let's say. So basically you search for contact pairs, which is open, which is closed, and so on, and it iterates like crazy, right? So everybody who does contact analysis knows that in the first step of the analysis, you want to allow a lot of iterations, because converging the contact for the analysis to actually start will take some time. So if you would be doing a nonlinear analysis, but a funny nonlinear analysis, let's say a multi-step linear analysis. So you have linear material, linear geometry, only contact. In step one, even though it's a perfectly linear analysis, in step one, you want to have a lot of possible iterations, just so the solver can converge the contact. And in step two, the contact is already converged. So sure, like the load will change something, but it's way easier. So you can have less iterations. And when you have nonlinear geometry, I assume that what you mean by this is that something deflects and start to contact whatever else is there in the model, not in step one, but somewhere. And then the problem is, where is this step where you need a lot of iterations for the contact to work? And well, you could essentially like brute force test it, right? Just divide the load into chunks, play the analysis. Initially, if there is no contact, nothing has to converge, so all is peachy. And then at some point, the analysis will throw a non-convergence at you and say, hey, in step 35, we really tried, but, sorry, right? And if you watch the outcome from the converge steps, you'll quickly realize when the contact starts to happen, and then you should give the allowable iterations there. Of course, you could potentially do like a lot of allowed iterations in every step, because the solver won't use the iterations that it doesn't need. Although, if something is off in the model and maybe you forgot to support or something else, you'll waste a lot of time waiting for the analysis to die because you allowed a lot of iterations for a process that never had a chance to actually work. At this point, I start to feel bad that I have like 3 pages of questions in front of me. So I'll just read another one and answer it, and then I will get back to the live questions, because it seems that those won't stop really. What should be the value of convergence tolerance, and do we need to change it, and if so, how to calculate it? I never do. I always use the default values, and being a blogger, it's a blessing really, because I know a lot of smart people, and someone who's way smarter than I am when it comes to mathematics of FEA looked me in the eye one day and said, look, if you don't have a PhD in mathematics, and I know you well enough to know that you don't want to mess with that. Just leave the default tolerances as they are and don't do anything. It's very complex mathematics if you want to do otherwise. And why I would love to help you, because I'm pretty certain that this is, you would be able to calculate something and understand this deeply. I'm not sufficiently mathematically inclined to learn that much about FEA and go there. So I won't be able to help with that really. How about defining a nonlinear static analysis with contact as a preload subcase for normal modes? Oh, you could do that, but in the end, the problem with that is that whatever is the final answer gets to the modes. So again, if you have a gap, it was closed. It's closed. If it's not, it's not. The model analysis that comes later will not see that it can detach from itself or not. Like, you really need a better nonlinear algorithm to deal with that, as far as I know. So yeah, it would be wonderful if this would work like that, but I highly doubt that it does. Hi from Singapore. Yeah, hi from Poland too. What is the meaning of convergence from nonlinear static analysis perspective? Well, convergence basically means that the solver checked internal energy, well, let's say work, of your model, and it's okay. So the principle of energy, as like the most common convergence tolerance, would be something like, if you apply a load, and in this place where you apply the load, the model moved, a certain work was done, the work of load on the formation. And the reaction of your model would be work of stresses on strains. So the material had a certain stress, this caused a certain strain, this is also work. So you have external work, load applied and the formation of the model, and internal work, the stresses, work on strain. And those two should be in equilibrium, because if they are in equilibrium, so the internal and external work are equal, then the model is stable. If not, something is off. And what solver does is actually computes, okay, this load was applied, this deformation is there, this deformations caused strain, the strain causes stress. Let's calculate the internal external work. And if this is equal, that's cool. If it's not, non-convergence, we need to try again, change something in the solution and iterate until the convergence is met. What you should know, however, is that the fact that the outcomes did converge does not mean that the answer is correct. It only means that it's in equilibrium. By this, I mean FEA doesn't lie, FEA doesn't cheat. Whatever you input as an input file for your solver was solved correctly. The thing is that whatever you see on your screen as an answer may not be the answer to the engineering problem that you've asked. Because for the answer to be meaningful, your model would have to be correctly constructed. So you need to have good supports, reasonable mesh, good loads, myriads of other things. And if all of those are good, then the converged outcome is okay, and you can analyze it. But if you stupidly support your model that is totally unrealistic, the answer will converge, and you will see the answers on your screen. But from the engineering perspective, those answers will be stupid because the model is wrongly supported, although the answer will in itself be correct because the model was calculated correctly. The problem was the input. So you did a model wrongly, and this makes the answers stupid. What is the impact of AI on FEM jobs? Man, I don't think there is any. I mean, seriously. Last week, I posted a nice animation of something failing, and a lot of people reacted with it, or was it even this week? And I've been called expert many, many times now. And I'm using algorithms that were developed in like, what, 70s? I think that Crisfield did in like 1972, Reeks did in 1971, maybe-ish. So it's like 50 years ago. And I'm using arc-length method to calculate post-failure models, and people say like, whoa, how did you do that? So yeah, I guess that I will start when I will go to a movie, to the cinema, that was played and directed by artificial intelligence, and I will like it. Because engineering is an art, and it's at least, if not way more, as difficult as directing movies. And sure, if you are doing something very simple and very repetitive, there is a chance that someone will, through sheer machine learning, like, teach the algorithm to do your work, and then the algorithm will do a super repeating job over and over again. Yes, that would be risky, but it's risky in all like aspects of life equally. But if you're doing engineer the way that I understand engineer, the art of solving difficult problems, I'm not afraid. I'm just not. And maybe one day I will look at this video and say like, who would thought the rise of machines and whatever, right? But yeah, it's not even on the list of things I worry about, man. What would be the best approach to estimate weld strength by combining FEA with analytical equations? What you should consider in building models and to assess the weld strength? Well, that's a question I really don't like because there is no good answer to it, to be honest with you. Firstly, we have to understand that analytical equations given in codes are based on research, and they usually assume that the stress can be uniformly distributed throughout the weld. By this, I mean, if you would take a plate in tension and you will weld it to something, the theory, the classical analytical solutions assume that the stress is uniform through the length of the weld. This is not the case, although the equations work because they are based on research. They were like benchmarked and all. So in FEA, you get the quote unquote real distribution of stress in weld, however you wish to define the weld, even if you don't define it at all, and just rigidly connect two things, right? If you have a plate and you pull, you know that in the corners the stress is higher, right? And this means that you don't get a uniform distribution of stress in FEA. And then the question is, okay, if I don't have a uniform distribution of stress, can I allow plastic redistribution of stress in the welds? Like clearly the algorithm that does analytical equations has to, because it assumes the equal distribution of stress throughout the length of the weld, right? But when you think on it, it's not that obvious. Like we all been taught that welds are not super ductile, or maybe the regions near the welds aren't, right? So that would be quite problematic. And as such, I would rather try to estimate the internal loads on the connection and then calculate welds with equations, then play around and model something extra with the welds. And I already mentioned the models I did for my nonlinear FEA course. And actually, part of the work that we're doing involves how to model the weld and estimate capacity and so on. Although that's not the main part, but it has to be there because it's welded. But I'm absolutely certain that whatever I will find is the best way to model it. My approach to it won't change, and it would be, let's assess the forces and calculate the weld by the code. It's way better, and I would believe those outcomes more than if I would do an FEA verification of a weld, because in the end, the problem is the scale. the welds are very small in very big structures, and if you want to get a decent outcomes, you would have to model them very accurately, which would make your model so big that you won't be able to compute it. So you have to simplify this, right? And then what can and cannot be simplified and why would be a very good question, but I don't have the answer. Nobody does, because it would require the amount of research required to do that would be crazy. And I think that in the end, something like reading the stress, assessing what the stress in the weld, and then calculated it by hand would be decent. Although the problem is that in FEA you get concentration of stresses, and you do not know if and to what degree you can even out the stress through the weld, because the analytical equations assume that you can, but it's not like explicitly explained. And that would be the biggest issue you're having here. Hey, thank you for the course. I attended both of them. Could you please advise where to study material models for polymers? Oh, hey, thanks. Well, first of all, thank you. I'm really glad that you like both courses. And when it comes to material models for polymers, I won't help you. I've never been in the space. I think that there is an American book. If you can, like, on the course forum, write a question. I will search for the link, because I found once a book. I think it was an American book that showed stress strain curves for like crazy amount of materials, and I actually forgot to order it. So like I will afterwards, I hope. And I can give you the link to the book. Like maybe it will have like sufficient amount of data. The problem is, like, funny enough, you already did the course, so it was explained there, but also in my free lecture on the nonlinear materials that you can sign up, that you can see the link on the screen. At the end of the video, there is this part where I talk about like research and testing material and basing your models on the tests. The problem is how repetitive the properties of your polymers are, whether you will get them from the same supplier, how this change, maybe because of the end of the year something, or like raw materials used, and maybe different suppliers or different regions have different properties, and then you would have to take all of that into account while building a material model. So that's an insane amount of effort. And maybe this was done, like, for steel, there are codes providing material models. Maybe there are codes that provide those models for polymers. But I was never into this enough to give you a good answer. So I'm afraid that I won't be able to help you all that much here. But write on the forum, and I will try to find the link for the book. So maybe at least that would help you. It's funny that sometimes you can see someone and someone you don't. So the LinkedIn user, interior relief is an option in Nastran that allows you to simulate unconstrained structures in a static analysis. One example of which can be used in object in flight. Static analysis via the finite element method requires the model to be constrained in all directions. If the model being analyzed is not fully constrained, yeah, that's true. And I think that there is also something called stiffness matrix stabilization that might be this, because the interior relief, inertial relief is a term I haven't met before, but you're right. That could be also how it's done. Although I think that even if you would stabilize the model, you would have to still like at least a bit constrain it. Maybe not. Like I've never dealt with anything in flight, so I won't be able to help here. Do you think one can be total SAE expert who knows both FEA and CFD and other numerical simulations? Is there a need for such a role in an industry? Oh, that's a nice question. All I can tell you is that it's quite likely that somewhere there is a guy with Asperger's syndrome so deep that he could do calculations like that in his head, most likely, assuming that he would be able to communicate with you to provide answers later on. So is it doable? Yeah, I guess. However, it's quite likely that I have an Asperger's syndrome, which makes me slightly on an autistic scale. And I've been in FEA for 15 years. And I still have so much to learn about FEA that I'm absolutely certain that toward the end of my career, I would still not know everything on FEA. And about CFD, I only know a guy who knows how to do CFD. That's like literally, that's all. I've never done a thing in CFD, and I will never do. And so this means that it's just too much to learn to know everything. The question is, do you need to know everything? And to that, the answer is most likely you don't. I have a PhD in shell stability, and most of I design pressure vessels, so there was like shell structures, right? But I rarely get deep enough into shell stability to reach the level on which I understand shell stability. Like maybe it's not the case because I just so used to knowing what I know that I don't see that. But I feel that it's very easy nowadays to go so deep into any particular field of engineering that you are reaching super understanding that's just not useful. And I feel that knowing everything about FEA might not be the best career choice, because the chance that you will be able to use much of what you know is very small. And I'm a pragmatic person, so I tend to learn things that I think that will be useful in the future. And not everything will, to me, right? Of course, you never kind of know what will be useful, but since I have my own company, to a certain degree, I can steer where the company goes and what it does, so I can follow my own interests. So I learn what I'm interested in, and then do a company thing that kind of follows that, right? So I started as a structural steel, and I designed beam steel structures, and now we're designing pressure vessels because it's more fun, and we do other crazy FEA stuff. So to this extent, learning what interests you would be a good call. But I don't think you could be expert is a very meaningless word nowadays. Like everybody can call themselves an expert, right? And if you can run a CFD analysis and see a colorful, flowy lines, does it make you an expert already, or you have to understand it? And to what extent do you have to understand it to be an expert, right? If you would have a practical knowledge as deep as I have in FEA, in CFD, I would say that would be sufficient. Although, look how I answered questions today. There were several things I had no idea about. And that's okay, because I don't do everything. And doing everything is almost impossible. And if you would do too much, you would be too shallow. So you want to find a nice equilibrium between going deep enough that it still matters what you know, but not too deep, because then the advanced stuff is more or less redundant in vast majority of cases. And then when you reach this depth, you just make the wider and wider selection of what you're doing, right? And will this circle of what I'm doing ever grow towards CFD? I don't think no, because I've mentally understood a few years ago that I will never learn it. And it's kind of like a belief I have in me now. So I guess that my answer would be no. And will the industry need such a role? Well, there definitely is the structure liquid interaction problems, right? So you calculate the CFD to give input to FEA, but you can do this with two people. And every of these two would be like an equal expert in respective field, so they can easily talk with one another and understand each other and do stuff. And having someone in between them, if the stuff would be very complex to the point that the CFD guy does not understand the FEA guy and vice versa, because the problem is so deep that the CFD guy understands too little of FEA and the FEA guy understands too little of CFD, and they just can't communicate. Having someone between them might be useful. Although I don't think that we are at the level where things are analyzed in a way that would make this a case. Because I think that if I would work with a CFD person, I would be able to explain what I need, how I need it, and so on. And I'm pretty certain I would be able to understand what they can provide if they would be like an equivalent in CFD. So it would be cool to know everything, right? But going sufficiently deep to be an expert and widening the field of what you can do would be a nice, that's the road I followed. I can't tell you if that's the best one. It's just the one that I've chosen, So that would be my answer. Is it possible to find jobs as FEM engineer in your country, since I'm from Peru? I don't know, mate. In my life, I have never searched for an FEA job. I have no experience in it. All I can tell you is that I hire folks, I was a lecturer for a decade, so I would ask my friends at the university who is like a good student on the top year, and ask my colleagues at the uni to give the student a contact number to me, so they call and we would talk, and I would hire those people. So if you're not from a local university, you obviously wouldn't be recruited by me, right? And I would actually like folks who work here to sit at my table at my office, because I like knowing people that work for me. We are a team and we spend time together and stuff like that. So, but like I'm a weird guy, I guess, and many businesses hire international people, and I guess that Poland is not a different country than any other in this regard. So finding a big company that hires people internationally, sure, it should be possible, and I definitely know that there are companies that cooperate with me in a way that every time they hire a new person, they buy them my courses and they do those courses, like those new employees do my courses. So I know that I'm constantly selling those courses this way. So clearly people get hired in FEA. Although, as I said, I never searched for an FEA job myself. So like, I'm terrible at it. I have no experience, man. So it's hard to say. But I don't think that Poland would be any different than any other European country in this regard. I think it would be quite similar, really. Oh, hey, Piotr. And yeah, the inertial relief, someone already mentioned. And so nice to see you, mate. I'm glad that you've made it. That's so cool that you're here. Thanks. Have I ever worked with geotechnical structures? No, I never did it. I mean, I have some vague ideas about it, mostly because a friend of mine did a PhD in bulk solid loads in silo structures. And since this is a bulk solid, then you actually model it as a ground, really. So he used Plaxis for it and all that. So I kind of saw how this works, but I'm a metal guy, and I'm doing weird stuff with metal structures, and that's what I like. I know a guy who does really crazy stuff with geotechnical. I never had the heart for it, man. I don't know why, but no, I didn't. Carl wrote that he thinks that Clump made things on all degrees of freedom. I actually read once in scientific articles what it means a classical pinned boundary condition for a shell, and there were like different options. So I'm very careful about it. But yeah, most likely you're right. Simulation results often need to be presented in a PowerPoint presentation, but this presentation is often also a simulation report. A simulation report makes a terrible presentation. How do you provide both? I do them independently, literally. So we would have like a 40 to 100 page report that has more words than pictures. Like there are pictures, like, nothing sells the work better than a nice plot, right? But I personally read and check every report that my company issues, and those have like thousands upon thousands of words where we describe what we did, how we did it, why we did it. There are illustrations and schematics showing like how this works. That would be a beautiful report. And how much of it is worthy of slides and the pictures? But in this case, I would actually like spend an extra few seconds and do the GIF animations, right? Because on the slide you can have the animation. You can't print an animation, right? So the animations on the slides really make me like going. I love that. So so that would be something I would really encourage. And I would never send a report as a PDF print of PowerPoint slides. Ugh, I can't fathom that, to be honest. Like that's not how I roll, and I definitely would do both separately. And funny enough, not like here when I do business, I'm mostly required to deliver the report, so the written picture part, and slides happen every 10th job maybe. Because I would insist on a meet because I like meeting with customers and discussing stuff. And when I do, I usually have the slides and to show off what we did and how and whatever. But it's the report that would be the thing that always happen, and slides happen occasionally. So, that's also a consideration. Can I consider instead the pressure load in a single point? Whoa, Lorenzo, I have no idea what you've asked before, but what would be a pressure load in a single point? That would be like a concentrate force anyway, right? So no, if you're talking about singularity, because I assume this is related to singularity somehow, I actually think that the outcome would be the same. Even if your software will actually allow you to do a pressure load in a single point, that wouldn't change a thing because it's still a single point. Again, about singularity, can you please explain if the strains that we obtain in a singular point in a nonlinear analysis are accurate? Because in a nonlinear analysis, we want to evaluate the strains. The stress may converge due to yielding. That's the problem. You may not necessarily get an accurate number of strain, but like to this end, you'll get to fracture mechanics pretty quickly. And I'm lucky because I rarely have to deal with like local singularities in places that matter in my models, because usually they are constructed in a way that I don't have problems like that. And that's a nice blessing because I don't have to worry about it all that much. And if you really care about accurate strains in a given region, then you would basically have to model it more accurately. And I know that simplification would lead to FEA showing you very high plastic strains, where in fact the crack propagation would not happen. And it most likely has something to do with fracture mechanics, but I haven't studied the field extensively yet. So I'm not going to go into like critical Griffith crack length and all that, because I'm only on the surface of this yet at this moment. But yeah, you can definitely get strains that are unreasonably high. And I did that in lab tests where FEA showed me on the simplified models, of course, like purposefully simplified to reach a very high plastic strains. You would actually get plastic strains that would indicate way after material rupture, and after the test, nothing happens. So, but again, I am building more accurate models, and some of me expect that those super accurate models with every detail and so on will simply show lower plastic strains. And it would be a modeling problem at that point. If a weld capacity calculated is shown to be passing when using simple beam model alongside standard calculations, but show high force distribution along the significant portion of the weld length when you use plate shell elements, that fails the weld capacity. Considering the high distribution is not a singularity, do you take the average distribution along the length, or how do you check the actual behavior, assuming you do not want to perform a linear elastic plastic analysis? In cases like this, the only honest answer I can give you is it depends on the case. And I've been in situations like that where I would, as I've mentioned already, I started designing structural steel. So I did a lot of beam models and welds and yada, yada, right? So if I would calculate the weld analytically, let's call it by hand. And then for whatever reason, I would do a FEA model of this connection. And I get outcomes that would not fit to the hand calculation scheme in a big way. And this can happen. Each case would be different. And sometimes I would say, oh, the FEA shows this and that. Okay, that's a problem. And sometimes I would say, nah, that's just like concentration or maybe something else, or maybe the rigidity of this or that. You know, there are reasons why this could happen that wouldn't be a problem. And this means that the honest answer is that in difficult cases, there are no governing rules which says whatever you encounter, the hand calculations are better, or whatever you encounter, the FEA is better. It's an understanding of what you're doing and seeing the flaws of each method and weighting which method in this particular case is more flawed than why. But for the most part, when I talked about developing a career, I've mentioned that it's good to not neglect things. I would actually search why there is a difference. Try to understand, like you have two different ways of solving the same problem and you got two drastically different answers. There must be a reason. Either the hand calculation model didn't foresaw something. It's possible. Or maybe your FEA model has something wrongly defined or too simplified or maybe too complex. Like there should be a reason why you've got drastically different answers. And understanding this reason will make it obvious for you which one of those is good in this particular case. And it's the understanding that would count, I'm afraid, not like a general rule that you can easily apply to whatever situation you will be in. So yeah, it would depend on the case, I'm afraid. And without seeing the hand calculations or doing the hand calculation and seeing the model, It would be impossible for me to answer you specifically, but also it would be dangerous because not knowing that I could be gravely mistaken, and it's a responsible job. So I don't want to get you in trouble. What is the advantage of finite element analysis over finite difference and finite volume methods? That's a awkwardly theoretical question, Danish. I have no idea, man. I mean, like, judging by the question, this is something that might be connected with university. And if so, asking a lecturer about that would be an awesome thing, because I don't know the answer. But I can tell you that I don't know a company that sells finite volume method solutions to engineering problems. Maybe they are. Like, I'm just using FEA. I think that it works and it's nice and I like it. It's a stupid argument, but maybe the volume methods are better. I do not know that. But yeah, it's like, I won't be able to help you here, I'm afraid. Negative eigenfrequencies in solution 105, meaning is there something fishy in my analysis? No, I don't know. If you would get a negative eigenvalue in buckling analysis, that would just mean that the load got reversed, right? And instead of positive load that you defined, the negative load was applied. So the difference, because effectively the eigen analysis would be the distance from zero in whichever direction, right? So most likely eigenfrequencies work the same way, but why would they be negative then? I don't know. I don't think I ever encountered this, man. But at the same time, I usually, when I'm set up the analysis, I usually say that I'm interested in outcomes that are from 0.00001 to 1,000. So this automatically outcludes all the negative values. And if you don't do it and leave the default 0, it can show you negative values. And I do it so often that it's likely that I just ignored those. But this also means that I wouldn't worry too much. Like if I would do linear buckling, I usually compare the model analysis to linear buckling, because to me those are quite similar, and I use a lot of linear buckling and I don't use a lot of model analysis. That's why I'm referencing linear buckling so often. If I would see a negative eigenvalue in log buckling analysis, I wouldn't sweat. That's okay. Oh yeah, so forces are in opposite direction from those models. Yeah, so that would be the same as in linear buckling in that case. Oh, okay, that's the same comment. What are the prerequisites to be able to understand the nonlinear FEA course? Do the course have recorded videos and live lessons? If recorded, how long they are accessed? Well, there are so many questions at once. My course will open in like 6 weeks, I think, in June. And what are the prerequisites? You should know something about FEA. That would be the honest answer. If you would be a fresher and you never used FEA before, you would be still able to follow my course easily, mostly because I learned nonlinear FEA first, and then I've learned about meshing loads and all that in my PhD. So it's doable, right? Like the course is done in such a way that you could see it and follow it through to the end, and you will learn nonlinear FEA because, funny enough, the linear behavior of your model is brutally independent on whether or not your model is correctly supported. Because like whether you support it correctly or not, it will still behave in a nonlinear way in this way or another. Right? So you can learn a lot. The problem is that I've met a lot of people who did like super complex analysis of a very poorly defined problems. And this is a problem of high mathematics. If you know how to do integrals and differential equations, it's absolutely obvious that you know how to add numbers, multiply, and do the square root, right? And in FEA, that's not obvious. You can be able to define a super complex nonlinear FEA analysis, but still have no idea how to properly support your model. It seems that supporting your model is easier and it's like more basic. So the thinking would be, oh, since I can do those complex things, I don't have to worry about the easy stuff. The problem is that's not the case. So I would say that it's actually psychologically better to learn the simple stuff first, how to support your model, how to load your model, mesh your model, things of this nature, because then when you actually do a model, it makes you understand what you're doing. And then you can advance, and based on that, you can learn nonlinear FEA. And you can learn the nonlinear FEA with the same amount of effort and almost with the same success without knowing the basics, But then you would really need a strong character to tell yourself, okay, I may be able to know how to do the advanced stuff, but I still need to learn the basics. It's actually very hard to start learning the basics without when you already know the advanced stuff. It's like a mental trick. You think better of yourself in some sense. So I know people who did it. I did it, right? But the more natural way would be to know the FEA basics, how to support mesh, load your model, and then do the advanced stuff. But you can do it the other way around. I just wouldn't necessarily recommend that. The nonlinear course doesn't have the videos for the lessons. It has like 15 hours of videos for the examples. And you have lifetime access to the courses, and all the lessons are written like articles on a blog. And there are every 2 weeks we have a 2-hour or 4-hour, depending on how long we talk, live meeting where we discuss stuff. I'm not sure if this qualifies as live lessons, because usually we discuss projects of people that attend the course that they do at work. So it's not like a class with slides, but rather a discussion about problems people actually encounter while learning and doing FEA. But it's definitely a live component. And to those meetings, formally you have access of 1 year, but like nobody lost their access yet. So, so it's a bit more complicated than that, but at least 1 year of the live lessons or the live office hours, if you will. LOL. Yeah, okay. LOL is cool. I take LOL any day. Hey, man. Do you know if gap elements in Ansys are treated as in Nastran? This question is connected to the article that you posted in Gap Elements some time ago. I do not know. I never used Ansys, to be honest, so I have no idea how they use gap elements. I would assume that they should work the same because, I mean, geez, it's a gap element. It's a rather simple thing, right? But maybe it's not. Like, I don't know that, so I won't be able to help you here. I'm modeling soil steel composite bridge by reinforcing the geotextile. I can try to calibrate parameters for geotextile. However, I couldn't get a good fit to field measurements unless I increase the strength of the geotextile by 1,000 times. What will you recommend to me? I have no idea, man. I never used geotextiles in my life, not to mention soil modeling and all that. So I just don't know. I hope that there are people working in the field, maybe some scientists all over the world, find someone who's decent and ask them. That's a very advanced thing you're doing, mate. Not many people will know the answers that you're searching for, and I don't think that you will find those in books. But searching for people that work in a field and maybe in academia as well, that do this stuff, that would be a good idea, I think. Is there any book that you can recommend which covers all the basics? I already talked about the books, and to be honest with you, I would rather recommend courses, mostly because the examples can be recorded as videos and you can see the discussion behind them. So courses would, I think, be better as long as they are like practical in nature, and the books just won't help you with the practical stuff this way. The medium just doesn't really allow that. Have you made missile model analysis? I never did anything missile related. I try to avoid such topics. So no, I didn't. Hi, Łukasz. Hey, Andrew. In your work, how often are you suggesting using delivering solutions with topology optimization? Are your clients willing to fabricate outcomes with more modern techniques to generate significant material savings? Andrew, first of all, this implies that the topology optimization would produce significant material changes. And I guess that the cost of introducing like the shapes, like, you know, the organic shapes you can get from topology optimization might be not worth the hassle. And no, I never used topology optimization myself. No, and funny enough, I was never asked about it. Like nobody ever approached me and say, hey, we have this problem, so would you be so kind and do a topology optimization for us? Like I would have to reply that I won't be able to, but I know a guy who does this. But yeah, I never worked in a field, and I was never asked about it. So I guess that this answers your question. Hey man, do you do offshore structural analysis in your company? Sometimes. If yes, how do you calculate environmental loads such as wind, wave, etc.? Do you get it as an input from customer, or do you calculate them separately and apply in FEA software? Thanks. I would ask this to be an input. I'm pretty certain that this is doable. I have a friend who actually works in a company where you design like offshore windmills, and he calculates like wave motions and stuff like that. I never did it because I never had to. And to me, those were the inputs that I would get. But I'm pretty certain that you could calculate that. That's just not a thing that I'm doing. Tomin asks, what is the difference between plate and membrane? I'm very careful about semantics here because, I like, for better or worse, I'm translating things to Polish as I answer the questions. So I can translate plate and membrane, but those two are quite well-known words. So I think that we both think about the same thing. The plate would be something that would rigidly react to the load and then, for a lack of better term, break. You could think about taking, like, I don't know if you have kids. I do. So when the kids build a castle, they would take two chairs and drop a blanket over them to make a roof, right? And then that would be a castle. You can go between the two chairs and you have a castle. Right? So a plate would be using a few wooden planks instead of a blanket as a roof. You can put a cup of tea on the planks and they will simply deflect. There will be like a bending stress in them. A membrane would be using a blanket as a roof. If you would put your mug on the roof, it would severely deflect, most likely spilling whatever you have in a mug. But this is because the blanket is so weak in bending that it can't really transfer whatever you have in bending. Instead, it deflects. As it deflects, it's getting longer and longer, and assuming that the supports can support the tensile load this elongation generates, it can be stable, entering something that it's called a membrane state. So everything that is flat and deforms a lot would be a membrane, like a tent. When you build a tent, it's basically straps of material hanging, right? And those kind of things would be membrane, and the plates would be like, slabs of concrete, steel plates, and so on. But it has to be said that, for instance, if you take a 10 millimeter plate of steel and cut half meter square out of it and weld it to something, and if you put something on it, that would act as a plate. That would be relatively rigid in bending, right? But if you take the same thickness of the plate and made like a 100 by 100 meter square and support it at the edges and put something in the middle, that would act as a membrane, because it's not nor the material nor the thickness of the element makes something a membrane, but rather the bending rigidity compared to the dimensions of the thing. You could think about it as slenderness. That would be the difference, I would say. Of course, some materials are terrible at being in membrane state because they are better at transferring compression, not tension. But in general, that would be the difference. How important to define residual disp or temps in manufacturing process as a pre-described condition? Most codes that I know of would not ask you to do that. So this is most likely not as critical. Although, if you're responsible for manufacturing process and you know that something significant would happen because of whatever reason, then you should use engineering judgment to like look at it and wonder whether or not this will play a role, right? You will have residual stresses after welding and of your model, but those are usually self-contained, which means that the average is zero. So when your structure yields, those will even out. And I think that this is why they are so often ignored. Although it's not that they are without an effect. Like when I was at university, they did a study where they cut through half height of beams to cut something they needed for another structure. And it is that when you cut the beam in half, it can relax the residual stresses and like bend itself, right? So it's not like those residual stresses do not exist. They do exist, although they are, as far as I know, mostly ignored in design. How did you transition from doing FEA into teaching FEA? I don't know which came first. That's a longer story, actually, because I was a lecturer for a decade at a university, and I learned FEA, the actual FEA, the nonlinear stuff that's important. I've learned it because I needed it for my PhD, and I hated it at the time, and it took me a lot of like trial and error stuff. But when I finally got it, I would still have like 7 years of academic career in front of me. By this, I mean that I've left after 7 years from defeating my PhD thesis. Or was it 8? Many years. So this means that for a long time at the university, I knew how to do FEA nicely, or at least I was getting better and better, and I was fascinated by it. So I had classes where I would show people how to do this in FEA and stuff. So the teaching, I guess that I was always a teacher. I remain at university not to do science but to teach. I was never a scientist, not a big one at least. Teaching was part of what I did, and I kind of like learn what I do and I teach what I did at the, like simultaneously. So I developed on both fronts at the same time. And back then, I had a company with two friends, and we did like structural steel. And I wanted to go toward the FEA. I realized that it's a good career, that there's money to be earned, and it's a good business to do FEA. And I tried to convince my business partners to go this route, and they didn't want to. And I started the blog mostly to like still be in touch with FEA and just do FEA. And a year later, I left my first company to start Enter FEA. And the blog was full swing back then. I realized that blogging takes me a lot of time, so I had to earn on it to make it work for me, really. So I did a first course, and it went very well. So I did a second course, it went even better. But at the same time, my company grew as well, and I did more and more complex things as I moved. So I'm not sure if it would be honest for me to say that I transitioned from doing FEA to teaching, because like I'm still developing in both directions as I go at the same time, really. So there was never like a split that happened. So yeah. Can we use Abacus to do piezo-resistive simulation? Mate, I don't even know what that is. I mean, I know what Abacus is. So just email the people who are local resellers of Abacus. They will tell you. I have no idea, mate. Sorry. Kindly tell us the difference between 106, 401, and 402 solvers for nonlinear analysis, and when to use which. Okay, I'm an old guy. I have gray hairs in my beard. So when I was starting with Nastran, because those numbers mean anything to me only because I use NX Nastran. And those are Nastran numbers for solvers. So if you're using Ansys or Abacus and you don't know what that is, don't worry. That's a very specific Nastran thing. When I started working with NX Nastran, there was no 401 and 402. There was 601 and 701. So that would be the advanced nonlinear solver and explicit advanced nonlinear solver. And 106, even back then, was treated as a legacy nonlinear solver. It was like a basic nonlinear thing you can have. And it does the basic nonlinear analysis. But for instance, you can't do contact and nonlinear anything using 106. If you have something that is nonlinear, like nonlinear geometry or nonlinear material, you can't have contact in this solver. So that would be a big disadvantage. And also, I rarely get to high strains because I work in metals, so the strain is limited. But I've heard that solution 106 is actually poor when you try to compute something with very high strain values. But I never went to the regions where that would be testable. So it's only a rumor I've heard, but I've heard it from few people. So there has to be something in it. To me, the advanced nonlinear solver is 601, which is Adina, and I still use it. I just bought when they discontinued it, I bought like an external license. And that would be a more advanced nonlinear solver. It allowed you to control the analysis better and maybe converge the analysis a bit quicker. So that would be the change. And 401 and 402, they introduced that 3 or 4 years ago, maybe 5 now. Time flies, man. And I only tested those. Those are like the Siemens stopped working with Adina. That's why they discontinued 601 and 701, and they developed an in-house solver. I think that they acquired some company to meddle with it. And those are technically the advanced nonlinear solvers of Siemens at this point. I've tested 401 and 402 like on the very release, like literally first month after release out of curiosity, and I've got a lot of problems with them. Like I just did sample test cases, and the answers I've got from the solver I didn't like. So I said, okay, maybe later. And I never got back to them. So I don't have any practical experience with 401 and 402, although I have to admit that one day I will test them. I just giving them time to do bug fix all the issues they may have with newly released solvers and so on. And a few years passed, and maybe a few more, and I will think like, okay, they most likely encountered most bugs. So let's take a look and see how this works. So far, I haven't simply tested it again, and the initial impression was bad. Although that being said, the 401 and 402 would most likely converge quicker, be easier to set up, and more robust, allow for contact, maybe even implicit, explicit analysis, things of this nature. So they are just more robust, and that would be the main difference. And when to use which, like, as long as you can get away with 106 and you don't have high strains, that would be awesome. And if you need anything that this solver can't do, 401 and 402 would be the case. And I think that there are two, because one of them includes inertia, like dynamic systems, where you have inertia of the and so the speed and time takes actual meaning in the analysis, and one of this doesn't. So if you have static, one of those would be enough, and if you have like actual dynamic time related analysis, then the other would be needed. But I I don't remember which one is which one. The membrane works in tension, plate in bending, shell combine both actions. Yes, Severin, that's kind of true, but at the same time, you could say that shell is just plate that is bent into a radius, and technically speaking, you could have a model that's a bit in membrane state and a bit in plate state. Would that be a membrane or a plate? The semantics here are very difficult, actually, and theory manuals tend to be very vague on those. You just get, this is a classical membrane, this is a classical plate, this is a classical shell, but realistically, the magic happens in between those classical fields, and that's why I'm always very considerate of semantics when we talk about things like that. And I would say that plate reacts in bending, yes, membrane reacts in tension, but depending on the slenderness, because you can have a plate in a certain slenderness that will partially respond with bending and partially respond in tension to the applied load, and that would be like a platomembrane, membranoplate. It's tricky. So giving names to things is actually difficult. Thank you for the reply. Also, I would like to know how shell differ from plate and membrane. Yeah, so to me, as I just said, perhaps Severin replied to your question and it somehow got mixed in my chat. But as I said, to me, the difference between shell and plate would be that shells are usually bent in a radius, at least in one direction. So it's not flat. It has a radius at least in one direction, and that would make a shell. And although there are software packages that have separate elements for shell elements and plate elements, so this is not what they mean in those cases, but reading a software manual in that case would explain what the solver thinks about whatever they called this way. And also the graphical user interfaces are usually translated not by the people who wrote the solver, so sometimes things just get weirdly translated. and that also happens. But checking manual would be like the best approach. Oh, hey, get it. How do you decide when the model is worth simplifying, and how far would you simplify a model? When would a hand calculation be better option than FEA? Get it. If I can calculate something by hand calculations are always better than FEA because they are quicker. And the thing is that in my mind, usually things explode into a lot of different problems. And when I look at something, I rarely get a feeling that hand calculations would be accurate enough to calculate a problem that I have with sufficient accuracy that I would be happy with the outcome. I'm usually like, nah, like that's too complicated. I won't be able to capture this with the equation, and that is ignored. I need to do FEA, right? So in some sense, this is a question of how deep you want to go into analyzing a problem. And I always go to the max. I never say, oh, no, I'm not doing that, right? Unless the scope of the work that I was tasked to do was set up in a way that I should not do something, I will do it. So with this in mind, I usually do FEA because very few problems are simple enough to reliably and nicely solve with hand calculations. But if I would have such a problem, I would definitely solve it by hand because it's quicker. Yeah, and but also doing hand calculations when you do FEA just to check if the FEA outcomes make any sense would be like a decent idea. And what is worth simplifying? Oh man, it's engineering judgment and experience, I guess. When I started, I did not simplify more things, and I saw in the outcomes of my analysis I did back then that those details that I decided to left in the model didn't play any role in the outcome. So that would be something that I'd say, okay, in this means I can simplify that. I don't have to care about this at all. But later in time, I would simply understand that, okay, I didn't ignore this last time and it didn't do anything, so I can ignore it this one. Or maybe I will, like, not ignore something for 5 times in a row. And in every analysis, I will look how this impacts the outcomes. And if there is no impact, it's clear that next time I will ignore it. And it's kind of like building like a know-how in my head, what can and cannot be ignored. And also engineering judgment is involved. There are no rules that I could give on a piece of paper, like 10 steps of simplifying a model or something like that. It's like, I don't follow rules like that. And I'm not a big fan of those because those usually can be misinterpreted and overused. And that's always a risk. Good afternoon. Yeah, to you too, mate. How easy to explain what is the meaning of integration points? That's okay. Wait a sec. I forgot about something. I did something super cool, and that is now I think that I can draw on the screen. So can I? Yes, I can. Oh, that's so cool. If you have a finite element, what FEA does, like this would be such a rough explanation. Bear with me here. You have several nodes, let's say, and then when you apply the external load, the load causes deformation, so your model will move, right? And since your model moved, each of the nodes will move. So let's say that it will move like this. This nodes go to there, this node goes here, here, there, right? So realistically, your element now looks like this, right? Since you know how it looked and you know how it looks now, you can technically say, okay, I can calculate strain in my element that would relate to the movement. Although you don't know the strain field yet, the only thing that you know is the values in the nodes, more or less. And you have shape functions of your element, the mathematical functions in your finite element that ties those values together. But this is not accurate. What they do is like, it's like mathematical thing, and they can be accurate only in places. Like a perfect accuracy is only in places, because if you think on it, there are like more elements everywhere, right? And this means that this node is not only related to this element, it's also related to this element, and that element, right? So whatever happens to this node is not only tied to whatever happens to this node with the element in question, but other things around it. So the answer in the nodes are not super coherent. And then you tie them up mathematically, and those functions produce a perfect outcome in something that's called integration point. So that would be a Gauss point of the element, right? You can have one of those, you may have four, those like you may have 9, I think. That would be the point on the surface of the element where you know the strain perfectly, right? And it is believed that those would be the most accurate FEA outcomes, and that the nodal values are like poorer. And then there would be scripts that would say, let's say that you have 4 Gauss points in an element, that you could extrapolate values to the edges and then extrapolate to the nodes to have better outcomes. You know, the fun is knowing 4 points, how can you give the answer to the entire element, right? And then, of course, the other element would also have its own 4 points. And then the answer in this node from this element would be different than the answer for the same node from this element. What to do, how to average that. So the Gauss points of the elements would be the places where you know the answer, but the magic happens in how do you like push this out on entire element and how this is averaged. But realistically speaking, if you have a good enough mesh, the quality of mesh is good, then you don't really have to worry about it because like the values you get in your element should be acceptable regardless on which value that you look. And if there are huge differences, then most likely you have a very big mesh, and having a better quality mesh would be like a better idea. And that was so cool. I got to draw something. Can we take a breakthrough FEA course anytime, or is there a particular you start? Some question for non-linear course. You can take the breakthrough FEA course anytime. You can just go to the website and sign up, and that's it. It's open non-stop. All the videos, lectures, everything, lessons, examples, they are available as soon as you start, and there's nothing. When it comes to non-linear course, it opens only like twice a year, and it will start June, so in like a month, maybe a month and a bit. Actually, in a month, more or less, I think. So that's when it starts, and next time it will start in autumn. I haven't decided when exactly yet. So this is how it looks. A pipe is bent. In reality, this has changed the material properties in the bend. What is the best way to rate this? Nonlinear analysis. Well, Alex, if you would like to do something like that and you're worried about the remaining plastic strains that happen in the pipe, the best way would be to model the bending. Just take the normal plate, quote unquote normal, and like flat, do an analysis that would wrap it around and check what the strains you have. And then you can do whatever else with the pipe you like. And the strains are already in your FEA model. It's a lot of work. I'm not sure if it's worth it, but it's doable. And that would be the only way I can think of. I think that I've read an article on what would be the proper material properties for cold form steel. You can Google for that. I'm pretty certain that you'll find it. And then you could have like a different material model for steel that was cold form. So that would be also a way, right? Read some scientific stuff. And if it's uniform, that's cool. The problem would be if you would have like a rectangular hollow section, right? It would have the flat places that were not cold form, and then the corners that were cold form. So you basically have one cross section with different materials, right? So that could be problematic. But if you need to be as accurate, using that material model might be a good idea too. Or modeling it and just remembering the strain and using the model again to calculate whatever you want to calculate. Can we model a beam using shell or plate elements? Yes, of course you can. Like if you're designing a steel building, like, you know, a whole 7 bays, 2 cranes, whatever, doing beams with plate models would take insane amount of effort. And I wouldn't recommend it. But if you make a beam model of a huge structure and one beam is super complex and you're not certain, you can model this particular beam with plate elements, model the supports where they are on top flange, bottom flange, web, whatever, right? Load it and apply the load in specific places on a flange, on the edge, in the corner, wherever you have the load, and then calculate it way more accurately than the beam model would allow. And that would make sense, and it's absolutely possible, and I've did it many, many times now. In nonlinear analysis, especially for contact nonlinearity, how stiffness matrix gets updated after each iteration? I don't know, man. I'm pretty certain there is a very robust mathematical solution for it, but I know how to converge a nonlinear contact in nonlinear analysis. I know how to properly set it up and analyze outcomes, but I do not know how solver checks this. I'm pretty certain that you can set up how often the stiffness matrix should be updated. So there is most likely a setup for contact iterations as well. But apart from that, the process itself, I do not know how this works. And I just never needed to learn that. In post-processing, are we to check the model or failure using true stress of the model or engineering stress? And FOS, factor of safety, right? Should be calculating using true yield or engineering yield strength. In most cases, that wouldn't make a much difference, assuming that you have like allowable strain on a reasonable steel grade level. So let's say 5%, because like the difference between true stress and true strain when the strain is small is so small that it's negligible on almost. And if you have like super high strains, by super high, I mean like 20, 30%, then using the true stress, true strain would matter. So it would make sense. But in those classical cases where you usually limit the plastic strains to like 3-5%, maybe the difference is so small that like I wouldn't sweat that too much. And I think that engineering values are good enough. But you know, like translating engineering values into true stress, true strain values is simple, and you can just do it and input whichever values you like. So it's not like you're missing a lot or gaining a lot. What I would say then is, I think that if you have doubts, and that's a rule I generally follow most of the time. If you have doubts, just do a model with both and compare the outcomes, and you will instantly see what's the difference there, and like you will be able to draw conclusions yourself. That's always a good idea, by the way. Kashi, you posted like 10 questions in a row. When to use large strain formulation and how does this affect our model? Well, I never used large strain. I never had to, because as I said, I'm limiting the strains in my structures to values that wouldn't need large strain. But I would, as such, I don't have much practical experience with large strain formulations, although I would try them sometimes if I had problems converging outcomes. I would say that the model will compute a bit longer, and that it would be more accurate if the strain values are actually higher, but I won't be able to give you a number above which level the large strain formulation is better. And that would definitely be problematic with solution 106, as I mentioned previously. Do you think topology optimization and generative analysis could be used mostly in the future where there will be machines and manufacture them easily? I don't know, man. I'm not a futurist, you know? I'm a very pragmatic guy. By this, I mean I'm here and now. And I usually try to think about stuff that really affects me currently. And that being said, I rarely think about the future in terms of what will the industry look like in 20 years, because I know that whatever will happen anyway, and we'll all have to adapt. So I don't sweat it. I know that I have in me to change whatever I need to change to adapt to whatever situation may be. That being said, I've started working in FEA 15 years ago. And I can honestly tell you that apart from the fact that machines got way faster in calculating stuff, and now I have to wait like 2 hours for a nonlinear run instead of 6 hours, not much have changed in my work. Like I've learned a lot, right? Sure, right? But realistically speaking, I've learned a lot, but I could have known that 15 years ago too. Right? So I guess that whatever will come, will come. But will topology optimization take over? I don't know, man. Like topology optimization is linear in nature, as far as I know. So a lot of complex things, most of what I design would never be solvable with topology optimization anyway. And that would be like a huge drawback. Although the simple stuff, maybe. I'm not saying no. I'm just trying not to predict the future and just trying to do my best today. Is there a possibility to rotate only one axis of a cylindrical COS, center of S? Coordinate system, but coordinate O system in Ansys? This would be great when using orthotropic material, or maybe a better idea. I don't use Ansys, so I won't be able to help you with this, and I'm not sure what COS is. But I'm pretty certain that whoever supplied you with Ansys have like technical support. Just ask them. It's a simple user case question. They will most likely know it. How is it that the structure is going through large displacement but not large strains? Like large displacement just affects, like the membrane strain, the state is a large displacement phenomenon, just like buckling is, right? And this can happen at low strains. This can happen at no plastic strains whatsoever in an elastic regime, right? So you don't have large strains at all, and stuff behaves in a nonlinear geometrical way. So large displacements are needed, and large strains would happen when you actually would have large strains in your material, and this can but doesn't have to be necessarily associated one with another. So that would be how I would approach it, at least. Yeah, I actually, Kasi, replied to your first question at the very beginning of the video. So when I stop, you can watch the recording and check the answer. Oh, exactly. I actually replied to your second question as well already, because I've got the list and I've printed it. I already talked about large strain as well. A simple plate designed using shell elements converges at a low load using 106 nonlinear analysis, but the same model fails to converge simply if the load is too high. Why is it so? Oh, because there is no equilibrium. Imagine that you have a material that would yield and deform into infinity when you apply 100 kilonewtons to the sample. You apply 99, you calculate FEA, everything's fine. You apply 101, so 1 kilonewton above the capacity. The solver calculates to 100. The specimen starts to yield, and it yields, and it yields, and it yields, and it yields, but the force is still 100. And the solver is still trying to apply 101 kilonewton, but it can't because there is no equilibrium in your structure that would allow 101 kilonewton of load because it's too weak. So it will never converge because the capacity of the system is too low. Of course, too low capacity is not the only way why your model would not converge. There are myriads of other things, starting from the yielding was too fast in finite elements and like a lot of other things, too big steps, too few iterations, whatever. But like by what you've described, I would be willing to guess that too low capacity would be one answer. Łukasz, will there be any promotion for the basic course in the near future? Oh man, like I will kill you here. I don't think so, but I don't know. Like I guess that I haven't increased the course price for like 2 years now, 3 years now. So considering the inflation, I guess that the nearest promotion would be, hey guys, in a month the course will be more expensive. So I don't think that the price will get lower than it is right now. But with absolute honesty, I don't have marketing plans reaching far enough to know the answer. Like, I don't know what I will do. Apart from the fact that in a month, I will actually start selling the nonlinear course. The rest is murky, but I wouldn't expect that. This I can tell you. Concerning cold rolled sections, how do we get the effective section to account for local buckling and global buckling effects? Man, this would be a very long discussion. There are code procedures that would allow you to calculate the effective cross-section that you will get. However, to take that into account in nonlinear FEA, for instance, you would like to model this with plates. instead of beams. Because in a beam, you can model the cross-section as with holes, right? But if you have an ineffective area in your cross-section, you can't just delete that, because that wouldn't be exactly the same thing. The best way would be to use nonlinear material, nonlinear geometry, just press play and it will buckle on its own, removing the parts of the model that would be ineffective in class 4, although that would take quite some time to compute. In my nonlinear course, I actually showed how this works. Like, I did a beam with web in class 4, and it would actually outclude the web, and it would locally buckle due to class 4. And so that's doable. It's just like, if you're having a lot of those in a big model with a lot of beams, then just manually remove the areas from the beam definition would be most likely quicker, although required like hand calculations. And perhaps there are softwares that calculate class 4 cross sections automatically, taking into account that, because technically what you lose depends on the forces. So it would change along the length of the beam, right? Like the higher loads you lose some cross section, the lower loads you don't. Right? So that would be problematic. Maybe there is a way to do this automatically now. I don't know. I rarely calculate class 4 things in bulk that would outclude straight out nonlinear analysis. So I don't know if that's automatically doable. Can you explain when you should use reduced integration elements? I studied that 15 years ago when I was like doing my PhD, because Abacus had a very nice manual about it. And sadly, I don't remember much. I think that this has to do with how the element calculates the stuff inside the element, the values like stresses, strains, and whatever. And if I recalled, it had to do something with hourglassing and fake rigidity, like when certain elements would poorly react to in-plane loads because they don't have the internal mathematics allowing them to deal with that. So a reduced integration would help. But I'm I don't like FEA theory sufficiently to have discussions about it that go in depth that would potentially help you with that. What I can, however, suggest is, if you're having a doubt, use both, compare outcomes, and try to understand why the outcomes are different, and quite likely they will be the same. So you'll know that in your particular case, this may not be the biggest issue. And this is usually how I approach those things. With irregular mesh flow, affect convergence the nonlinear contact problem? Nonlinear problem in general, yes. Contact specifically, possibly. I'm not I always do very nice meshes, so I never tested how bad meshes impact the outcomes, because I knew that I will do nice meshes anyway. But if I would have to guess, I would say yes. Again, the easiest way to check it is make a nice mesh and then make an ugly mesh and just compute both models and check how the convergence look like, how long the analysis would run, and so on. My experience tells me that it's usually better to make nicer meshes, because you speed up the analysis, you get nicer outcomes, and you don't have to argue with people watching your analysis why this mesh is sufficiently good. If you do very good mesh, everybody's happy. So that would make it important. And this week I've posted a pin that yielded, and I've got 3 or 4 separate comments saying, "Wow, that's a very nice mesh." So it works on so many levels when you have a nicely meshed model. So I would highly advise you to do it, regardless if this affects the convergence or not. But at the same time, I would say that most likely it does. What to do if moment equilibrium equations are not converging in a nonlinear contact and material problems? Non-convergence may have so many different reasons, mate, that it's impossible to say. It depends on how usually the software, when it calculates, it shows how the convergence looks like. Is it going downward, upward, or whatever? Let's assume that your problem is properly defined and everything is fine. All you need to do is increase the amount of iterations allowed for the problem and just wait, and it will converge eventually. But just as well, the problem may lie in something completely different, like you wrongly supported or wrongly loaded your model, or there is some other thing that preventing convergence in general, contact or not. And then allowing more and more iterations will not solve this problem. So firstly, check if your model is supported correctly, meshed correctly, loaded correctly, that everything is there and makes sense. And then if it does, increasing the amount of iterations may help you. But as I said, without seeing the model, it's impossible to answer a question like that. Is there any need to know what happens behind the solver in order to get errors resolved quickly? If not, then up to what extent we should know the maths to be a good FEA engineer? That's a personal question, really. And I have a very strong opinion on it, but I wrote an article on a blog. I did several interviews in people on YouTube. You can watch those for the answers. My approach to this would be this. You definitely need to know the conclusions that come from theory. You don't have to learn the theory to know the conclusions. Someone can tell you stuff. You can trial and error things. You can reason things out. You don't necessarily need to know how to integrate shape functions of a third order element to know that you need a nice mesh and how the nice mesh looks like for your FEA to make sense. And what you need is to get the practical knowledge of how to do FEA. Theory is one of the roads to get there, although not obvious one, because you can learn all the theory and still be unable to derive the conclusions from all the equations, right? Because it's not knowing the equations, it's drawing the conclusions that counts. And if you won't be able to draw the practical conclusions from the equations, learning the equations is plain stupid. Because unless, of course, you want to, work as a FEA solver developer, that's a nice career, but it has nothing to do with FEA design, right? It's an IT job, and in which case, knowing everything about every equation is a must. But assuming that you want to do what I do, so design with FEA, the theory is not needed as long as you know the conclusions, and you can basically get the conclusions from experience, from someone else, like from courses, for instance, or you can learn theory and try to conclude the conclusions yourself. And depending on your character, you will prefer one way or another. I'm a tinkerer, so I will experiment and talk with people and learn from them. And this is how I learned. I never studied theory. I don't think I would be able to solve a differential equation without access to internet. Like maybe like the super simple one I would, but like as soon as it gets like beyond the first lecture of the first semester, I'm done. Right. And yet I feel an expert in nonlinear FEA, and I know what I'm doing because it's the conclusions that you need. But that also means that you need to know the conclusions. And so I don't want to lightly say you don't need theory at all, because you need the conclusions and like the practical of how to correctly do FEA. And this can be derived from theory. I just think that learning from others, from courses and experimenting is easier and better. But it's also my character, right? Like I talked recently with a guy our conversation is on LinkedIn, no, on YouTube, sorry, and he would tell me, no, I love reading like theory manuals. This is how I learn. And I was like, okay, I would just tinker, and he's like, that's okay too, right? So there are various ways, and depending on how you get to the knowledge, the answer would depend. But the fact that you need to know the practical conclusions of it is undeniable. And it's only one of the few ways you can get those. So depending whether you choose it or not, the answer will depend on it. Why in nonlinear contact problem we get different stress if we define yield point of the material in material plasticity data and without defining material yield value? Well, because you have a different material model, mate. Like if you define the yield value, then your solver most likely assumes bilinear model. And then with higher strengths, you get just the yield stress because it's a bilinear model. If you don't define it, you have a linear model. So you will have much higher stresses because it's a linear material model. So sign up to my free FEA lecture. You can see the link on the screen right now. And during this lecture, I explained this in depth in like 1 hour video. And I think that it will answer all your questions way better than I can do here in 2 minutes. What is the cost of your nonlinear course? It's like $1,300 more or less. Consteel, maybe. Thanks. You're welcome. It's so funny when you see those things like out of context. Have you ever seen the kind of stuff the Idea Statica can do with MG nonlinearity, MG material geometrical, I assume, and how apparently easy to set up a single it is to use? Are you happy that those methods are becoming more available, or do you see some kind of danger in it? Nico, that's a wonderful question. When Idea Statica started, I reached out to the guy who's the owner of the company and said that, look, you're starting with a very nice programs. And I can do benchmarking for you. I'm good at FEA. I can do this for free. All I want you is to say that people like Łukasz from Enter FEA did the benchmarking for us, and we can compare our simplified models because Idea Statica doesn't use FEA. It has its own method that's specific. Like, all I can tell you is the friend tested it out, and actually the outcomes of the analysis would depend on the parameter called acceptable strain in your model, and it would actually produce a different Idea Statica outcomes because I don't want to call this FEA outcomes. So there are gimmicks, right? And they were not interested in me benchmarking those. And I had colleagues using Idea Statica that know very good how to calculate connections, and oftentimes that would get some stupid outcomes. And they would reach out to those people and they say, like, we've benchmarked it, we have manuals, it's your problem, realistically. But it was a few years ago. I'm absolutely certain that Idea Statica is developing very quickly. And because it's a very popular program with wonderful marketing. So clearly they have the budget to expand and do stuff. And do I see this as a danger? That methods are easily available? To some extent, yes. Not because the method, like, not danger to myself or to my business, or I have more competition on the market. Like, nah, that's not a danger. The danger lies with techno priests from Warhammer 40,000. I'm a big fan of Warhammer Fantasy. It's a a book realm for fantasy novels, and there is a multiverse called Warhammer 40,000, which would be like a super far future. And the setup is that humanity figured out spaceships that can navigate themselves and repair themselves and fuel themselves and travel across galaxies. And we long forgot how they operate. We have no idea how to build one. And to travel from a planet to a planet, a priest, like a literal religious priest, will go to the machine and made a sacrifice to the spirit of the machine for the spacecraft to travel folks from one planet to another. And the priest does not understand that he just gives directions to AI where they want to go. They don't remember that at all. And there is a risk associated with simplifying stuff too much, because if everything happens automatically, nobody cares how it's done. And there's a risk, because you should understand how this is done and why it is done this way. So I feel that as long as people understand it, simple tools are better. And if you dump them down too much, people will lose the understanding of it, and that would be a tragedy. So there is a risk, but hopefully people will just learn enough and be good with that. That would be cool. Do you accept Bitcoin? No, I don't. I'm an old guy. I don't use Bitcoin. Whew, okay. I still have like a lot of questions on the cards, but I think that I actually stumbled upon many of those as I explained yours. So I hope that's okay. And that the answers that I've got were there. I was aiming to wrap it up in 2 hours. So I guess that we are at the finish line. And yeah, what I can say is thank you for being here with me. I really appreciate it, and I really like the live events. It's so cool that we got to be here, and that I actually run to the very end of the questions in the chat. And I'm always happy when I manage to do it in a time that I assume. So that's awesome. And yeah, thank you for being here. If you want, you can sign up to the free FEA lecture that I did on nonlinear material. I think that you can learn a lot of cool things there. And yeah, thank you so much. Have a wonderful day and see you around. All the best. Oh, Adam just wrote, excellent Warhammer analogy. I have seen it often where procedures become rituals where steps are replicated with understanding. Very bad in FEA. Oh yeah, of course. And Warhammer, it's like, it really helps in life. So being a fantasy geek is a good thing when you're an engineer, I guess. But I really like that I'm not the only Warhammer geek around. That's so good to know. Yeah, so folks, have a wonderful day. See you around, and I'm sure we'll be in touch. Take care.